In this video, we're going to keep practicing with our Gibbs free energy calculations. So it may come as no surprise to you that just like with enthalpy and entropy, that because Gibbs free energy is a state function, we can also use coupled reactions, and we can use standard energies in order to calculate Gibbs free energy for a multitude of reactions. So that's what we're going to try here. So in this reaction shown here, this is unburned hydrocarbons and oxygen reacting to form ozone, and this is what happens on really warm days in like LA and leads to that really hazy smog that ends up in the valley. So this is a reaction that we don't really like happening, but we're going to see what happens with this reaction and how we can calculate the delta G. So if we know the delta G of formation for our products and reactants, then we can sum them in the same manner we have for entropy and enthalpy. So what we need to know for this problem are the delta G's of formation for our compounds. Okay, now that we have our values, we can look at our method of calculating these. So the standard delta G of a reaction is going to be the sum of the delta G of formation of our products minus the sum of the delta G of formation of our reactants. And again, we have to take into account our stoichiometric coefficients. So our delta G naught is going to be negative 394.4 plus 2 times negative 228.6 plus 4 times 163.2, and that is delta G of our products. And from that we will subtract negative 50.5, because just like with our oxygen, the enthalpy, it is also the Gibbs free energy for a pure substance is 0. So, and it's a pure element in its standard state, that's 0. And so the standard state for oxygen is not elemental oxygen, it's molecular oxygen. So that's why for molecular oxygen it's 0. Okay, so let's add all of these up together, and we see we get negative 198.8 kilojoules plus 50.5 kilojoules, and that is negative 148.3 kilojoules. So let's say I want to calculate delta G for this reaction. The problem is that I don't know the delta G of formation for all of these compounds. And so fortunately, just like we do with enthalpy, since this is a state function, it doesn't matter how you get there to the end, it just matters that where the start is and where the finish is. What you can do is break this down into component reactions that you do know the delta G for, and you can manipulate them so that you can get the right answer. So let's see that if we have any known delta G reaction values and see what we can get. Okay, so these are 3 reactions that I know my delta G of formation. So let's see if I can manipulate these in some way. So there are some rules. So if you have to multiply a chemical reaction by any factor, then you have to multiply the delta G by that factor. So what do I mean by that? Well, we want 3 carbon solid, so we're probably going to have to multiply this by 3, and if that's the case, then we have to multiply this value by 3. In the same fashion, if we reverse a chemical reaction, then we need to reverse the sign on delta G. Up here, propane is on the product side, but here it is on the reactant side. So if we end up reversing this reaction, then we have to change the sign on delta G. finally, we have to sum up the free energies of the reactions for all of these steps. So let's take a look at this. So since we know that this has propane as a reactant and we want propane to be on the product side, let's start by reversing that one. So I'm going to put my summation ones in blue down here so that you can follow how they're different. So I'm going to go 3 CO2 plus 4 water, well, 4 water vapor, going to C3H8 plus oxygen. And the delta G for that is now positive 2074 kilojoules. Okay. Now I know that I have, like I had pointed out earlier, there's a 3 here and there's not a 3 here, so let's go ahead and multiply that by 3. So what I'm going to do is write this as 3 carbon plus 3 O2 going to 3 CO2. And my delta G of my reaction is 3 times negative 394.4 kilojoules, which is equal to negative 1183 kilojoules. All right. And last, I see that I've got a 2 of the H2 here. And I've got a 4 here. So let's go ahead and multiply this guy by 2. So I've got 4 H2 plus 2 O2 going to 4 H2O. And then my delta G of my reaction is going to be 2 times negative 457.1, which is equal to negative 914.2. Now let's start canceling and see if we've got it all. So I see a 3 CO2 here and a 3 CO2 here, so I can cross those out. I see 3 O2 and 2 O2 and a 5 O2, so those look to be gone. And I've got 4 H2O and 4 H2O. So it looks like I'm left with 3 carbons. Let's not make that look terrible. 3 carbons plus 4 hydrogen gas going to C3H8 gas. So double check. It looks like we're good. And then we'll add up our values. So it's plus 2074. And then we have a negative 1183, a negative 914.2, and that leaves us with a negative 23 kilojoules for the delta G of the reaction.